All right, so today we have Matteo Sacchi, who will tell us about anomalies, generalized symmetries, and compactification. Take it away.
Thank you, Julius. Very happy to finally be back at the Quiver meeting. So I'm going to tell you about some results from these two papers. The first one is from last year in collaboration with Orsel and Gabi Zafrir. And the second one is more recent from last month. And for the second paper, also Emily Nardoni and Yongqin Zheng joined us. So let me introduce to you what are the main topics, what are going to be the main topics of this talk. I will talk about generalized symmetries. So we have seen, like in recent years, that there's been a sort of revolution in the topic of symmetries, and in particular, starting from this paper that appeared by now 10 years ago, many generalizations of the usual notion of symmetry have been put forward. And we know that this is very useful in quantum field theory because symmetries allow us to constrain the dynamics of a QFT, especially in the non-perturbative regime. So for example, when you have a symmetry, you're going to have some selection rules that constrain various correlation functions in your theory. And also associated to symmetries, you have anomalies. So I'm going to talk a lot about anomalies. And these are powerful because they are invariant along the RG flow. So this allows us to study sectors, regimes of the theory in which, for example, the theory is strongly coupled. So it's very difficult to analyze by just computing them in a weakly coupled regime of the theory. So some of the generalized symmetries that are going to appear in my talk are higher form symmetries, which act on extended operators rather than local operators. Higher group symmetries, which mix higher form symmetries of different degrees, and non-invertible symmetries, which instead are characterized by the fact that their generators, they don't satisfy an ordinary group like fusion rule. I'm not going to give you a thorough review of all these topics in generalized symmetries, but I will still remind you of the key ideas that are needed to understand what I'm going to talk about. When we study QFTs, another approach that is very useful is the one of compactification. So when I say compactification, what I have in mind is that you can start with some higher dimensional theory, TD, and compactify some of its space-time directions. Usually in this compactification, we also specify some extra data, which could be, for example, holonomies, fluxes, and so on for gauge fields. And the idea is that now we can flow to energies which are much smaller than the inverse of the compactification scale. So in a sense, this is triggering an RG flow across dimensions. And so at low energies, what we end up is with an effective lower dimensional theory. The reason why this construction is interesting is because it typically allows us to understand various properties of the lower dimensional theory in terms of properties of the higher dimensional one and this compactification data. And actually, this is the general logic, but actually in some cases, we can even reverse the logic. So sometimes we can understand the various things about the lower dimensional theory, and we can use this to infer something about the higher dimensional one. So what I'm going to be interested in this talk is the relationship between compactifications and symmetries. So for ordinary zero-form symmetries, this is something that's been studied a lot. And naively, the expectation in this picture is that the higher and the lower dimensional theory should have the same symmetries. But this is a very naive expectation, and it can fail mainly because of two phenomena. So on the one hand, you can have accidental symmetries. And so by this, I mean symmetries that are not present in the higher dimensional theory and that they emerge in the RG flow as we flow to low energies. And for example, what can happen is that the lower dimensional theory has more symmetries of the higher dimensional one, and some of this symmetry might come from the isometry of the compact space. So, for example, something that will appear in my talk is that if you compactify on a two-sphere, then the lower dimensional theory has an accidental SU2 global symmetry that comes from the isometry of the S2. But some other phenomena that can appear is that some of the symmetries of the higher dimensional theory may end up acting trivially in the lower dimensional theory. So they trivialize along the RG flow. So this is a sort of opposite situation in which instead the lower dimensional theory has less symmetries than the higher dimensional one. But this situation, we can analyze it better, and especially we can rule it out using anomalies. Because as I said, anomalies are invariant along the RG flow. So if there's a symmetry that has some non-trivial anomaly, then this symmetry cannot act trivially in the infrared. Especially there's going to be some degree of freedom in the infrared that transforms under this symmetry, and so that accounts for this anomaly. So this is to show that already for zero-form symmetries, this story can be subtle. And what I'm going to investigate in this talk is what happens instead to generalized symmetries and to some types of anomalies under compactification. So this is the main topic of my talk. I also want to make a comment about supersymmetry. So most of the ideas that I'm going to explain in this talk actually apply more generally, so also to non-supersymmetric theories. However, for me, it's useful to consider supersymmetric theories. In fact, all the examples that I'm going to show will be supersymmetric. But this is just because with supersymmetry, we know we have more control on these theories. And these types of compactifications that have been studied and understood a lot for supersymmetric theories. So for me, just supersymmetric theories just represent a good laboratory to test the ideas that I'm gonna explain. Craig raised his hand.
Yes. Hi, Matteo. Hi. Quick question just to make sure I'm following here. So if I have a 4D theory with like a U1 zero form symmetry and a U1 cubed anomaly, and I put this thing in an S1, how do you argue that the U1 must act faithfully on the 3D theory just because of the 4D anomaly? I don't see that immediately.
No. I mean, that's not well, in that case, you wouldn't have the anomaly in 3 dimensions, like in the strict 3D limit. So you can still have the anomaly if you keep the radius to be finite, but in the strict R20 limit, you don't have the anomaly. So what I was saying is just that yeah, I mean, it's going to be a bit clearer when I explain again. But if you have a non-trivial anomaly, well, I'm going to explain how you do that, essentially. But you take the anomaly of the higher dimensional theory, you compactify it, and if it's still non-trivial in lower dimensions, then the symmetry cannot act trivially.
So you need some kind of argument that the anomaly in higher dimensions maps to some other anomaly in lower dimensions. That's the argument?
Yeah, that's going to be one of the topics of the talk. Yes.
All right, thank you.
No worries. Yeah, so I was talking about supersymmetric theories. Let me also tell you something that you can do for supersymmetric theories that people did a lot studied a lot in the literature. So in the previous slide, I wasn't requiring anything about the higher dimensional theory. In particular, I wasn't requiring that it is a conformal theory. But something that you can do is you start from a theory in higher dimension, which is supersymmetric, but also conformal. And you do the same procedure. So you compactify on some compact space and you add some extra data. And at low energies, you end up with some lower dimensional SCFT. Now, a question that you can ask yourself is whether you can reach the same lower dimensional SCFT, but with another RG flow that lives only in this lower number of dimensions. So you ask yourself if you can find a UV theory in lower dimensions that flows to the same fixed point in the infrared. And in general, we would like this UV theory to admit some Lagrangian description. So this is going to make things quite interesting. And in particular, this is interesting because, as I said, from the compactification picture, so this first RG flow, we can understand the various properties of this lower dimensional SCFT. But these properties might not be trivial at all from the perspective of the lower dimensional UV theory. And so this allows you to understand many non-trivial infrared properties that these UV Lagrangians should possess. Okay, before going into the core of the talk, I wanted to just give you the TLDR of my talk. So what are the main takeaways? So the talk is going to be roughly divided in 2 parts that correspond to the 2 papers that I mentioned at the beginning. So in the first part, I will show you how the anomaly theory that encodes all the anomalies of your QFT, of the higher and the lower dimensional theory, when you study compactification, are related by integration over the compact space. So this is basically what Craig was asking before. And in particular, I'll show you that this idea can be applied also to higher form symmetries and to finite symmetries, and not just to continuous zero form symmetries, which is something that was already known. In the second part, I will instead discuss a little bit what happens to various generalized symmetries under compactification. So I will consider a very specific setup that I will spell out later. But the key idea is that under certain assumptions, all of these generalized symmetries trivialize, but you can still have an imprint of these structures in the lower dimensional theory in terms of Hooft anomalies and various symmetry breaking patterns. Okay, is there any question so far? Okay, if there are no questions, let me review quickly the idea of anomaly polynomial and anomaly theory, since they're going to play an important role in this talk. So we know that an anomaly is basically a failure of a partition function in being invariant under a background gauge transformation. So you can compute your partition function as a function of a background gauge field for a global symmetry, and you can ask yourself what happens to the partition function under a background gauge transformation. And if you have an anomaly, basically the partition function is not invariant, but you pick up an exponential of this form. Now, for continuous symmetries, and so this is going to apply especially in even dimensional theories. This anomaly can be encoded in a so-called anomaly polynomial. So the anomaly polynomial, you can think of it as a theory that lives in two higher dimensions. So it's this ID plus 2, and it's related to the anomaly ID via the so-called descent equations. And the anomaly polynomial is going to be just a purely classical theory, because it's only it only depends on the background field for global symmetries, which are non-dynamical. For finite symmetries, you cannot define an anomaly polynomial, but you can define a so-called anomaly theory. So the anomaly theory also exists for continuous symmetries, and in that case, you can think of it as going like only using half of the descent equations. But if you have finite symmetries, you can still define an anomaly theory. So this anomaly theory lives only in one higher dimension, and in this higher dimensional manifold such that its boundary is your spacetime. And so in general, this anomaly theory has the property that under a background gauge transformation, it's also not invariant, but its variation exactly compensates the transformation of the partition function. So one way to understand it is that if you take this object, so if you multiply the partition function by the exponential of the anomaly theory, then you get a partition function that's completely gauge invariant. So what happens to the anomaly polynomial under a compactification? Well, the idea is that, as I said, the anomaly polynomial is a classical theory. So you don't expect any interesting RG flow for the anomaly polynomial. And that's essentially why there is one way to understand why anomalies are RG invariant. So if you have the anomaly polynomial of the higher dimensional theory, this ID plus 2, and the one of the lower dimensional theory, this can be related by just integrating over the compact space. And in this relation, I'm assuming that there is no boundary for the compact space. Otherwise, you would have a contribution from the various punctures. So this is something that's quite well established. And in this picture that I was showing you before, it's something that you can test explicitly, because on the one hand, you can obtain the anomaly polynomial of this lower dimensional SCFT from the one of the higher dimensional SCFT by this integration. On the other hand, you can also compute the anomaly polynomial in this Lagrangian UV theory, and you can verify that the two expressions match exactly. So what about finite symmetries? So in particular, what if one of these, either the higher or the lower dimensional theory, are odd dimensional? Well, the anomaly, in this case, as I said, you should use the anomaly theory, but also the anomaly theory is a classical theory, so also this theory should be invariant along the RG flow. And so the general idea is that you can also perform this operation of integration also for the anomaly theory. Again, assuming that the compact space has no boundary. So this is essentially the key idea. And what we did in our paper with Or and Gabi was to test this idea in some examples in which the compactification is is under control. So what do I mean by under control? Well, what I mean is that we have some other independent tool to determine what are these lower dimensional UV theories. And so what we can do is, as I said, on the one hand, do this integration. So for this first RG flow. And then you can check that the result of this integration reproduces the anomaly of the lower dimensional theory. And so this is going to be a check of this equation that I wrote in the box. So what is this setup of compactifications? These are the compactification of 5D n equal 1 SCFTs on Riemann surfaces with a topological twist so that you preserve n equal to 2 supersymmetry in 3 dimension. So this type of compactifications, we studied them a lot in some previous paper with Or and Gabi, and so we could borrow some results from these previous papers to test this idea of the integration of the anomaly theory. So let me give you one example in which this idea, we verified that this idea indeed works. So you can start in 5 dimension with the E1 theory. In this case, I'm considering the rank 1 E1 theory. And we know quite a few properties now about this theory. So we know that it has an SO3 flavor symmetry, zero form symmetry. We know that it has a Z2 one form symmetry. And we also know that there is a mixed anomaly between these two symmetries. And since we have it's a 5-dimensional theory, this mixed anomaly is going to be encoded in a 6-dimensional anomaly theory that takes this form. I don't want to spend too much time in explaining the details of this expression because I will not need it, but just to give you an idea, so this W2 is the second Stiefel-Whitney class of the SO3 symmetry. So it's a characteristic class that distinguishes SU2 and SO3 bundles. And B, for the entire of my talk, B will always be a background field for a one-form symmetry. And P of B is the Pontryagin, the so-called Pontryagin square. So it's an operation to take a square of this background field.
Matteo?
Yes?
Is there a reason you don't go through 4 dimensions?
Well, no, there's no actual reason. Actually, like to derive the 3D models is actually something that we partially do. Because, for example, here I want to study compactification on a torus. I can think of the torus, I can cut it open as a tube. And then basically, so the actual building block is going to be the compactification on a tube or a sphere with 2 punctures. And to figure out what is the result of this compactification, you sort of study domain walls between 4D theories. So I'm not explaining this entire derivation of these 3D models because this is some previous paper, but it's actually something that we do going through 4 dimensions. So here I'm just presenting the net result of what happens if you go from 5D to 3D. Okay, so as I said, I want to compactify this theory on a torus. And in the compactification, I also turn on a flux for the U1 Cartan of the SO3 flavor symmetry. And this 3D UV Lagrangian theory that I was talking about before, in this case, is this circular quiver theory. So here I'm drawing it for a flux F equal to 2, but for general flux, it's just a bigger circular quiver. So this is a 3D n equal to 2 quiver. Each circle node is an SU2 gauge symmetry, and there are alternating Chern-Simons levels, +1 and -3. The edges are n equal to 2 chiral multiplets in bifundamental representations, and the crosses, they're just some details. Here they represent some chiral fields that are singlets under the gauge symmetry, but they don't matter too much for this discussion. Since you have n equal to 2 supersymmetry, you should also specify a superpotential, which in this case is a monopole superpotential. And it's basically the monopoles with magnetic flux +1 and -1 under any pair of adjacent gauge nodes. So it's going to be +1 and -1, then another term is +1, -1, and so on. You go along the entire quiver. The job of this monopole superpotential is that it breaks the 4 independent U1 symmetries that you would have for each edge of the quiver to a diagonal combination, which is what I call U1C. So in this drawing, I'm also encoding the charges of the fields under this C symmetry as this exponent of the fugacity, and under the R symmetry as the exponent of the fugacity X. So this quiver has a U1 C flavor symmetry, which is what we expect, because we started with a theory with an SO3 flavor symmetry, and we compactified with a flux that broke it to the U1 cartan. Moreover, this theory also has a Z2 one-form symmetry that comes because the diagonal Z2 center of all the SU2 gauge nodes is not acts trivially on the matter fields. And so this also matches nicely with the 5D picture. And finally, you can compute the anomaly between these two theories, which in this case is going to be a 4-dimensional anomaly theory. So you have these two results, and what you can show explicitly is that this 6-dimensional anomaly theory reduces to the 4-dimensional one upon doing explicitly this integration on the T2.
The superpotential is quartic?
The superpotential is a monopole superpotential. So it's linear in this monopole. So you're going to have a monopole with flux, say, magnetic flux +1 for this node and -1 for this node. This is one of the terms in the superpotential. And then you have one such monopole for any pair of adjacent nodes in the quiver. So like in this drawing, you're going to have 4 monopole superpotentials.
So it does not depend on the edges of the quiver.
No, it doesn't involve these chiral multiplets. It only involves the monopoles.
Only monopoles.
Yes.
And
yes.
How are the R charges determined for the bifundamental?
You just use the usual formula for the charges of a monopole. Something that I didn't say is that this monopole should be dressed. Yeah, sorry. Probably this is what we were asking. So these are dressed monopoles. So indeed, they actually involve these chiral fields, because the bare monopole is not going to be gauge invariant due to the Chern-Simons level.
Yes, but how do you determine the? So the X is also a dressed operator with monopole?
So this C to the 1/2, X to the 2/3 is the charge of this link, of this chiral.
So how those charges are determined?
Well, they are determined because initially you just assign generic charges, and then you compute the charges of this monopole that you want to turn on in the superpotential. And so you can figure out explicitly how the monopole superpotential breaks the symmetries.
But
so before turning...
Since the bifundamentals don't show up in the superpotential, how can you determine them? You said it's not.
Well, first of all, they actually appear in a way because they are used to dress the monopole.
Okay.
And second, the monopoles are charged under the same symmetries under which the chirals transform. So the monopoles are going to break the symmetries under which also the chirals transform.
I see. Okay, so it's from the superpotential. Fine.
Yes.
Okay.
Yeah. The short answer is that these charges are determined just by the superpotential.
Okay, thank you.
Okay, yeah. So what I was saying is that something that we show explicitly in the paper is that you can relate these two anomalies by doing this compactification on T2. This requires some gymnastics with characteristic classes, but and also it requires that you have this flux for the flavor symmetry, and also that you have an holonomy for the one-form symmetry. This is quite crucial. So I'm not explaining explicitly this derivation, but you can roughly understand that the W2 of SO3 becomes the C1 of its U1 cartan mod 2. And then of this B squared, you lose 1B because you do the integration over the T2. And so you only have 1B in lower dimension, but you pick up this F from this holonomy. So this is one example in which we checked that this idea works. In the paper, we have many more examples. But to conclude this first part, I would like just to make some comments, some general comments about our work. So the first one is that so what we analyzed were these 5D to 3D compactifications. But as I said, the idea of integrating the anomaly theory should apply more generally. So we tested it in this setup, but it's applicable in more general setups. If you focus instead on these 5D to 3D compactifications, you can actually have 2 points of view. So the one that I had so far is that you assume that you know the 5D anomaly. So then you integrate it, you have an expectation for the 3D anomaly, and then you can check that this UV Lagrangian theory reproduces the same anomaly. So from this perspective, basically this compactification of the anomaly theory gives you a new tool to check this type of compactifications. But what we observed actually in our paper is that in many cases, we knew the result of the compactification, because as I said, we have some other tools to figure out these 3D theories. And in these 3D theories, we can compute some anomalies, and we can argue what is the 5D anomaly that should reproduce the 3D anomaly. But the 5D anomaly, in many cases that we studied, was actually not known before. So in a sense, you can reverse the logic and use the 3D results, the 3D computations, to argue for some anomaly in the 5-dimensional theory. So I want to just flash one example of this. So if you instead consider the E0 theory, this theory has no flavor symmetry, but it still has an SU2R symmetry. And also we know that it has a Z3 one-form symmetry. And basically what we managed to predict for this theory is that there should be a mixed anomaly between these two symmetries that is encoded by this anomaly theory. So again, the way this anomaly theory is derived is because we know that some 3D model that describes the compactification of this theory. We know the anomalies in this 3D model, and this is the only anomaly in 5D that can reproduce the same anomalies. Okay, so this is all I wanted to tell you about the first part on the integration of the anomaly theory. So it's a good moment to stop for questions, if there are any. Okay, so let me move on to the second part, where I want to discuss the compactification of some generalized symmetries. So as I said, for this, we consider a very specific setup. So this setup is the one of 4-dimensional theories that have a U1 magnetic one-form symmetry that is associated to a U1 factor in the gauge group. And also they have some flavor symmetry. So at least they should have a U1 flavor symmetry. As I said, what I'm gonna say can apply to any theory that satisfies this property, but my prototypical example will be the minimally supersymmetric SQCD theory with UNC gauge group and NF flavors. So the first thing that I want to discuss is what are the type of anomalies that you can have that involve these symmetries. So the first anomaly is a cubic anomaly in the flavor symmetry. So remember, we're in 4 dimensions, we're dealing with continuous symmetries, so all these anomalies are encoded by a 6-form anomaly polynomial. So this anomaly is what we usually call a Hooft anomaly, and it represents an obstruction to gauging this U1F symmetry. But here I will not be really actually interested in this type of anomalies. Instead, I'm interested in mixed anomalies with also this U1G gauge symmetry. So what you can have is an anomaly that is quadratic in the flavor symmetry and linear in the gauge symmetry. And because of this anomaly, the conservation equation of the flavor symmetry current is going to be modified in this way. However, this modification is not too dramatic because you can immediately see that if you turn off the background field for the flavor symmetry, then the current is still conserved. But so this means that the symmetry is not actually broken by this type of anomaly. But there's still, of course, an imprint of this anomaly. And as discussed in this paper by Cordova, Dumitrescu, and Intriligator, to see what's this imprint, you have to turn on the background field for the flavor symmetry, which I'm calling AF, but also a background field for the magnetic one-form symmetry that I'm calling B. And because of this anomaly, what happens is that if you do a background gauge transformation for the flavor symmetry, then also the background for the one-form symmetry should transform. So this is basically the relation that's the hallmark of a two-group for continuous symmetries. And finally, the last situation is the one in which you have an anomaly that's linear in the flavor symmetry and quadratic in the gauge symmetry. So in this case, the situation is instead more dramatic, because the conservation equation now it's violated in such a way that, like, on the right-hand side now, only the gauge field for the dynamical gauge symmetry appears. So this symmetry is actually broken. This anomaly is what is known as an AVJ anomaly, and the standard law for years has been that it implies that the U1F symmetry is broken to some finite subgroup whose order depends on the anomaly coefficient. So it's going to be a ZK symmetry. However, what has been understood more recently is that you can actually retain more transformations inside U1, and not just these ZK transformations. And these are in particular transformations labeled by rational angles. But the price that you have to pay is that these transformations are not invertible. So now the understanding is that if you have an AVJ anomaly, the U1F symmetry has an invertible ZK subgroup, but also a Q mod Z non-invertible.
Excellent. Let's continue.
Okay, so the question, the question that I want to ask is what happens to these generalized symmetry structures upon compactification? This is something, so in our paper, we studied compactification on an S1 to 3 dimension and on S2 to 2 dimensions, but for this talk, I'll only talk about the S2 compactification. And as I said, the results that I'm gonna explain are more general, but we check them explicitly in a supersymmetric example in which we compactify for the n=1 theories with a topological twist on S2 so that you preserve 0,2 supersymmetry in 2 dimensions. So this is a type of
the typical argument for 4 dimensions is to dismiss the U1 gauge group. You started by saying UNC gauge theory. And so why do you use UNC rather than SUNC?
So in all this entire discussion, what I was looking at were anomalies for the U1G part of the gauge group. So for example, in particular, to have a linear anomaly in G, this has to be a U1 symmetry. So the reason why I take UNC is that it has a U1 factor.
I see. Okay. Yes, thank you.
Okay. So this is the type of compactifications in which we tested the ideas that we're going to discuss, because they were studied a lot in the past, and so we understand them pretty well. So let me review a little bit about these compactifications. So one efficient way to study them is using the T2 times S2 partition function. So if you have a Lagrangian theory, which is the case that I'm considering, you can compute this partition function with localization. And it takes the following schematic form. So it's basically a matrix integral. The integrand here, it's completely determined if you know the field content of your theory. Then you have an integral, but I don't want to discuss these details because actually it doesn't play any role in my discussion. The important part is that you also have a summation over the fluxes for the gauge symmetry through the two-sphere. So because of Dirac quantization condition, these take values in the co-weight lattice of the gauge group. So an observation that's been made in the past is that if you focus on a single term in this sum, so essentially if you fix the flux for the gauge symmetry, then the corresponding integral exactly takes the form of the elliptic genus of some Lagrangian to the 0,2 theory, which can also be computed. So it also has this matrix integral form as shown in these papers. So the interpretation of this is that if you take for the theory and you compactify it on an S2, then you don't get in general a single 2-dimensional theory, but a direct sum of disjoint 2-dimensional theory. And it's useful to use this partition function because we can read off the field content of each of these two-dimensional theories just from this matrix integral. So in this way, it has been possible, for example, to recover the 2D triality of Gukov and Putrov starting from the cyber duality in 4 dimension. And towards the end of the talk, I'm going to review this a little bit, this derivation. So this is general. Now, if you focus on this setup in which we have a U1 magnetic one-form symmetry, then you can ask yourself what happens to this one-form symmetry when you compactify to 2D. So for this, you can look at the defect that generates the one-form symmetry. So this is a two-dimensional defect that's obtained by integrating the star of the current for the magnetic symmetry, which is just the star of F for the gauge symmetry, on some two-dimensional manifold. So what you can do is take this two-dimensional defect and wrap it on DS2. So this is what I'm writing down here. Now, if you pick just one of these theories in this direct sum that I talked about, since the gauge flux is fixed, and since basically the topological defect is the exponential of the flux, then it means that in each of these theories, the one-form symmetry acts trivially, because now the defect is just like a phase. So another way to understand this is that each of these theories in the direct sum are disjoint universes, and these universes, they're labeled by the charge under the one-form symmetry. So the moment you pick one universe, you are in a sector in which the charge under the one-form symmetry is fixed, and so the symmetry acts trivially. And as a consequence, all the generalized symmetries that I discussed before, they trivialize in each of these 2D theories, particularly the two groups and the non-invertible symmetries. However, what we observed in our paper is that there is still an imprint of these generalized symmetries in terms of either Hooft anomalies or symmetry breakings of this U1F flavor symmetry in 2 dimensions. So this is what I want to explain. So one useful perspective to understand this is using the anomaly polynomial. So what you can do is exactly what I explained in the first part. You can take the terms in the anomaly polynomial that I showed you before and integrate them on S2, imposing that you can have either a gauge or a flavor flux. So let's try to do that and see what happens. So if you consider the anomalies that were related to the two groups, because they are linear in the gauge symmetry, then you can decide to either integrate the field strength for the flavor symmetry, and so you produce a flavor flux and you get a term of this form, or you can integrate the C1 of G. So you're going to produce in general 2 terms. The first term is an ABJ anomaly in 2 dimensions that tells you that the U1F flavor symmetry in 2D is broken to a finite symmetry whose order is given by kappa, that was the anomaly coefficient, times the flavor flux. The second term is instead a pure Hooft anomaly for the flavor symmetry. And again, now the anomaly in 2D is not just kappa, but it is multiplied by the gauge flux mg. If you instead compactify the term of the anomaly polynomial that was related to a non-invertible symmetry, again, in principle, you produce 2 different terms. But the first term, you can see that's a pure gauge anomaly in 2 dimensions. So in order for the theory to be gauge anomaly free in 2 dimensions, you have to set the flavor flux equal to 0. But this is something that essentially we already knew. So if you want to compactify theory, a theory on an S2, you cannot turn on a flux for a symmetry that's involved in an ABJ anomaly. However, you can still have the second term when you have a non-trivial flux for the gauge symmetry. And this is again an ABJ anomaly in 2D. So again, this second term implies that the flavor symmetry is broken to some finite symmetry that now it's K times the gauge flux. So what we did in the paper was to check explicitly this idea for the n=1 UNC SQCD. So what do I mean by checking? So what I mean is that on the one hand, we have these expectations for the anomalies in the 2D theory, knowing the anomalies in 4D. And we can check that this expectation is correct because using the partition function perspective, we can find explicit Lagrangians for the 2D theories. And so we can compute the anomalies in these 2D Lagrangian theories and verify that they reproduce the results from the previous slide. And we did this check, and we figured out, we observed that indeed these observations, they work. But there's a major problem with this. If you remember, the justification that I gave for why you can integrate the anomaly polynomial is because anomalies are RG invariants. But anomalies for gauge symmetries, they should not be preserved along the RG flow. So what the hell am I doing here? What I just did, it should not work. So why do we observe that it actually works?
But before that, I have a question. How much information from the partition function do you need to know? You don't need the complete form of the partition function, right?
So for me, it's enough to have this matrix integral expression, because as I said, then I can just look at this integral, but think of it as an elliptic genus. And so from this expression, if you give me such a matrix integral, I can tell you what's the gauge group in 2D, what are the chiral fields, the Fermi fields, the gauge fields, and so on.
Mm-hmm.
And also, like, you can refine this partition function with fugacities for global symmetry. So I can also figure out what are the symmetries in 2D and what are the charges of all these fields under the symmetries.
I see. So that's equivalent to having a Lagrangian, I suspect.
Yeah, essentially, yes.
Mm-hmm. So you could have done this also by operating on the 4-dimensional Lagrangian and getting the 2-dimensional Lagrangian?
Yeah. Yeah.
Mm-hmm.
Yeah, absolutely. It's just, yeah, for me, it's just a convenient way to do it, because
okay.
it's essentially what has been done in this paper. So now I can just borrow the results that they found, and
Mm-hmm. I see.
Yeah.
Okay. Thank you. And you keep supersymmetry, right? In the previous case, you were breaking supersymmetry. This case,
yes, exactly. So this is a detail that I didn't say, but you always have a flux for the R symmetry on DS2, which is a topological twist that preserves 0,2 in 2 dimensions.
oh, you do break supersymmetry. I see. Mm.
Yeah, you partially break it, but not completely. Yeah,
Okay.
If you start with 4D n equal 1, the best you can do is have 0,2 in 2D. So you break half of the supersymmetries.
I see. Okay. Yes.
Yeah.
Thank you.
Okay, so here I wanted to give also another perspective on this issue, which is that you can think of starting with a theory where the G symmetry is not gauged, so it's a flavor symmetry. And essentially what we are studying is an RG flow that consists of 2 steps. First, gauging G, and then after gauging G, you will compactify down to 2 dimensions. But you can think of reversing the order of these 2 operations. And so you compactify first, but now you're compactifying a theory where the G symmetry is a flavor symmetry. So Hooft anomaly matching actually works. And then you gauge the U1G symmetry in 2 dimensions. However, another way to phrase the issue is that you don't expect these 2 operations, the gauging and the compactification, to commute. So these 2 RG flow, in general, they will end up a priori at 2 distinct fixed points, 2 distinct final points. So the resolution to this puzzle is that the 2D observations that I derived before using the anomaly polynomial perspective, so the Hooft anomalies and the symmetry breaking in 2D, you can also understand them completely by just talking about the generalized symmetries that you had in 4D. And so sort of forgetting about all the gauge anomalies. And since anomalies are invariant under this compactification, unless you do something that explicitly breaks them, it's more just like all these observations are actually justified this way. So for the rest of the talk, what I want to give you is some other argument to recover exactly the results of the previous slide, but that now use these generalized symmetries. So the first thing that you can do is study this situation in which you have a 2 group in 2 dimensions, and you compactify with a flavor flux. So what you do, you just take the transformation of the background field for the one-form symmetry B and integrate it over S2. And so you get such a type of transformation for phi that's defined as the integral over S2 of B. But the exponential of phi is an holonomy for the one-form symmetry, which of course you're always free to turn on when you do a compactification. But if you change the holonomy, you're actually changing the theory. So you would like the holonomy to stay invariant under such a transformation. So this is gonna constrain what are the transformation parameters for the flavor symmetry. And in particular, the only transformations that now are allowed are these Z kappa times MF transformations. So this is a way using the two group to understand why the U1F symmetry is broken to this finite symmetry. And you can use a similar argument with the background fields to also argue that instead, if you compactify a 4D theory with a two group, but in the presence of a flux for the gauge symmetry, then you get an Hooft anomaly in 2D whose order, whose anomaly coefficient is exactly kappa times mg. And this is actually something that was already discussed in the paper in the two group paper. I can give you also another sort of pictorial understanding of this second situation using the topological defects. So what you can do is in 4 dimensions, remember we have a two group symmetry. So how do you understand the two group in terms of the topological symmetries? Well, you consider a junction of 3 such defects. So these G's are defects for the zero form symmetry. And so the topological defects that generate them, they are 3-dimensional. So in this drawing, I'm drawing them as lines, but they also span the 2 directions that are orthogonal to the scheme that I'm not drawing. And the two group tells you that if you perform an F move on such a junction of defects, then you produce a defect for the one-form symmetry. The defect for the one-form symmetry is 2-dimensional, so here it's like a point because it only spans the 2 direction that I'm not drawing. Now, what you can do is take this picture and reduce it over S2. So on the left-hand side, you get a similar junction because you can think of wrapping these 3-dimensional defects GI on the S2. So basically, the 2 directions that I'm not drawing now they're gonna be these S2. And so in 2 dimensions, these defects are just lines. So they're still defects for zero form symmetries, but in 2 dimensions. The one-form symmetry instead becomes, the one-form symmetry defect, it becomes just a point-like because it was wrapping the S2 that I'm using for the compactification. Moreover, if you remember, the defect for the one-form symmetry was the integral of the gauge flux. So if I compactify with the gauge flux, basically this one-form symmetry defect just becomes a phase in 2 dimensions. So what I get in 2D is this other picture in which if I take a junction of zero form symmetry defects and I perform an F move, I pick up a phase. And so this means that in 2 dimensions, you have an anomaly for the flavor symmetry. So in this way, you can understand again, let me say it again. So if you have a two group in 2D and you compactify with a gauge flux, you get a pure Hooft anomaly in 2 dimensions for the flavor symmetry. The last type of situation that I was considering was the one of an ABJ anomaly in the presence of a gauge flux. And for this, again, we can use the perspective of the topological defects. So let me first consider as a warm-up the defects for the invertible ZK part of U1F. So these are 3-dimensional defects, as I said before. And if you forget for a moment about this second term, the way you usually construct these defects are by integrating the star of the current. And basically, the topological nature of the defect is a consequence of the fact that the current is conserved. So this star F is this star J is equal to 0. But the current here is not conserved. So the defect, if you don't put this term, the defect is not topological. So what you can do is to construct a topological defect by adding this second term. So you sort of dress the defect in this way. here A is the gauge field for the 4D gauge symmetry, the U1G symmetry. So this defect is still gauge invariant because this term is a 3D Chern-Simons action with a properly quantized Chern-Simons level. And now it's topological because this was the modification of the conservation equation of the flavor symmetry current. And so it implies that this whole exponent is closed. And so you can run the same argument to show that this defect, this dress defect, is now topological. So these are the defects that generate this invertible ZK subgroup of U1F. And with this expression, what you can do is, so here what I'm doing is wrapping the defect on the S2 that I'm using for the compactification and on an S1 inside the 2D spacetime. And you can explicitly do the integral over S2 of this expression. And you can already understand that when you integrate dA, you're going to pick up the gauge flux. So if you do this explicit integration, these for the defects, they basically reduce to defects in 2D that generate an invertible ZK symmetry. However, if you remember, I told you that if you compactify in the presence of this ABJ anomaly, what you get in 2D is not a ZK invertible symmetry, but a ZK times mg. So how do we get this the remaining transformation of this bigger group? To do that, you have to look at the defects for the non-invertible Q mod Z symmetry. So these defects are constructed sort of similarly. Again, you integrate the star of F, but since this is not conserved, you have to dress this defect. But now the dressing is a bit more complicated. You have to dress it by using this 3D QFT AN, P that lives entirely on the defect. So this is the result of the papers that I showed you before. So in those papers, they showed you that this defect is now topological, gauge invariant, but now it's non-invertible because essentially the dressing is done with these 3D TQFTs. But even if these theories are more complicated, luckily, all of these theories, they always admit Lagrangian description as an abelian Chern-Simons theory. So for example, if P is equal to 1, this Chern-Simons theory is U1 level n. So essentially what you are doing is adding a dynamical gauge field that lives only on the defect with a Chern-Simons action like this, and that has a coupling to its Zn one-form symmetry of this type. And when you dress the defect, you identify the background field for the Zn one-form symmetry with the 4D field strength. But these Lagrangian descriptions can be found for generic N and P. For example, you can find it in this recent paper. Using this Lagrangian description, you can again do explicitly the integration over S2. And what you get are again some defects that generate some invertible finite symmetry in 2D. But now you get all the ZK times mg transformations. So in this way, you can see that this 4D non-invertible symmetry reduces to an invertible ZK times mg symmetry in 2 dimensions. So with these approaches, you can, let me tell you again the logic. So I derived some results using the anomaly polynomial perspective, but you can derive the same results using the perspective of the generalized symmetries, which is now more justified than using the gauge anomalies. So the last thing that I want to discuss is some comment about this derivation of the 2D triality from the 4D cyber duality. So here I'm going to review very quickly this derivation, and the idea is that in our paper, we applied all the ideas that I explained so far to get a better and more detailed understanding of this duality and this derivation. So to derive the triality, what you start with in 4D is cyber duality for UNC gauge group, which can be obtained from the usual cyber duality for SUNC by gauging the U1 baryonic symmetry. But we also add some fields in the determinant representation of UNC. So these are fields that transform only under this U1 baryonic symmetry that I gauged. And the reason is because the R symmetry is involved in an anomaly with the baryonic symmetry. So after you gauge the U1 baryonic symmetry, the R symmetry would be involved in an ABJ anomaly. But I want to compactify this theory to 2D on an S2 with a topological twist. That's a flux for the R symmetry. And I told you before that if you compactify with a flux for a symmetry that's involved in an ABJ anomaly, then you get a pure gauge anomaly in 2D. So that's something that I want to avoid. And so to remedy for this, I add this chiral fit such that the R symmetry is now non-anomalous. But if you add these fields, you of course introduce new global symmetries. And in particular, there's going to be a U1 global symmetry that's still involved in an ABJ anomaly. So this model now I can compactify it with a topological twist, and it still has this ABJ anomaly that's associated to the non-invertible symmetry. So what has been showed is that if you take this duality and you reduce it on S2, and you focus on the zero gauge flux sector, then you get exactly the 2D triality of Gadde-Gukov and Putrov, which I'm summarizing here with this quiver diagram. So this is a quiver for a 2D 0,2 theory. So now there are also dashed edges because they denote Fermi multiplets. And also the wiggle line is representing these fields in the determinant representation. And 1 and 2 and then 3 are three numbers that add up to an F. And in fact, the product of these three global symmetries is a subgroup of the SUNF flavor symmetry that you have in 4D. And yeah, let me also say that this looks like a duality, but actually it's a triality because from this theory, so you can see that from here to here, you basically swapped M3 and M2. And now here you can apply again the same duality by swapping M2 and M1. So you get a third duality frame. So some new things that we understood about this triality and its derivation are the following. So you can see that in 2D you have an additional SU2 symmetry that's accidental in this compactification perspective. And what we showed is that this SU2 symmetry comes from the isometry of the S2. Another thing that we discussed is that, so in the previous discussion about the triality, people only looked at the continuous symmetries. But if you are more careful, you can see that there is a U1 axial symmetry. I call it axial because it's a symmetry under which all the fundamental fields have the same charge +1. This U1 axial symmetry in 2D is involved in an ABJ anomaly with the gauge symmetry that breaks it to this finite subgroup. And so what we did is we checked that this finite symmetry also maps nicely across the triality. For example, you can match all the anomalies in all the triality frames. And moreover, now we can understand this breaking in 2D as a consequence of a two-group in the original four-dimensional theory. Because if you look at the anomalies in the 4D theory, you will see that there's an anomaly like this. So it's a linear in the gauge symmetry. And that's why it's an anomaly related to a two-group. And it's linear in the axial and in the R symmetry. Now, in the compactification, you turn on this flux for the R symmetry because you want to do the topological twist. And so if you integrate this anomaly, this term of the anomaly polynomial, you exactly reproduce the ABJ anomaly that you observe in the 2D model, and that breaks the axial symmetry in this way. Okay, let me conclude by repeating again what's the TLDR of my talk. So in the first part, I showed you this idea of integration of the anomaly theory when we perform a compactification from a higher dimensional theory to a lower dimensional one. So the anomaly theories of these two theories can be related by integration of the anomaly theory on the compact space. In the second part, I discussed how in certain types of compactifications, all the generalized symmetries of these 4D models trivialize. But I also showed you that in some cases, there can still be an imprint of these generalized symmetries in the lower dimensional theory in terms of Hooft anomalies and various symmetry breaking patterns. Let me mention some results that we had in the second paper, the more recent one, on the compactification of generalized symmetries that I didn't manage to include in the talk. So I told you that we studied also compactification on S1. However, I prefer to drop this discussion because it's somewhat more boring, because again, all these generalized symmetries, they trivialize, and there's really not a particular imprint in the three-dimensional theories. And also what I didn't discuss is that actually you can, all these derivations of results that I showed you with anomaly polynomial, background fields, and topological defects, you can rederive them in a more sort of unified way using the symmetry TFT. And I didn't discuss this because the logic is essentially the same that I explained for the anomaly theory. So you can take the symmetry TFT for continuous symmetries that's been understood quite recently. In particular, we use the form of the symmetry TFT from this paper. You can take that symmetry TFT and do this integration over DS2 and get a symmetry TFT for the 2D theory that exactly has the features that I discussed in this talk. Let me also mention some open questions, again, more related to this second paper on the compactification of generalized symmetries. So you can, like most of what I told you, heavily relied on the fact that we have a Lagrangian description for the theories that I studied. So of course, it would be interesting to understand like what happens in low Lagrangian cases and which of my arguments still apply and can be generalized and which cannot. Another question is whether we can study other type of compactifications in which we can still retain some of the generalized symmetries in the lower dimensional theory. And finally, so for these generalized symmetries, I only consider cases in which all the symmetries were continuous. So of course, there's a question about what happens for generalized symmetries involving finite symmetries. Again, some of the arguments that I used, they still go through, but some others, they don't. Okay, so this is all I wanted to say, and thank you for the attention.
All right, let's thank Matteo, who despite some technical difficulties gave his talk. Do we have questions? Okay, it seems we had quite a few questions already during the talk. If we have no immediate questions, I would say let's thank Matteo again.
Thank you.
And we can go off the record.